Everyone, come on in.
I just sent you a text, so you can disregard that.
Okay, you worried about me not showing up?
Yeah, yeah, I was. We
Gotcha.
hadn't heard from you. So, we're having lab tomorrow then, right? Or,
Actually,
that's not
yes.
you. I do the Wednesday lab in the
Yeah,
morning. So,
yeah, we're doing it
um,
at regular time. That's why I didn't send an email to tell everybody to come late or anything.
yeah, yeah, tomorrow lab, right?
Yeah,
Yeah.
but it's not for lab. It's all for lecture. So if you're content with what you're getting here, just you don't even need to come tomorrow morning. You personally.
Okay, yeah, I've done all the homework and I did part of everything that's due on the 28th. Am I supposed to complete all of it? I completed half of it.
On the lab.
I mean, for the actual homeworks on Pearson.
Oh yeah, yeah. You should complete them all, but like I said, the homework's not that critical to the overall course grade. So
I mean, the ones for the 28th that said they're all due on the 28th,
oh
like 10 assignments.
yeah, if it's on the chapters that we haven't covered yet, and we're just on like 28 now, so don't worry about that. Not
Oh,
until
I did most of it. I didn't know and I hadn't heard from you, so I went ahead and did a lot of it.
that's okay. I'll
But
probably be giving extra credit for people that finished it when it was originally due. So that's fine.
uh, yeah, not the homeworks, the stuff that was due at the last day of class.
Gotcha.
I did a lot of that.
Yeah.
I didn't know, and I just was finishing up all the math because I'm in a lot of math now. I'm finally understood the integral, the infinity thing. I was just looking
Gotcha.
at it the wrong way. Every time it said infinity, my mind would do a Cobb's Douglas production function. And I'm just like, there's no such thing as infinity. But I realized it was just a mental block. So I'm over that. Um, the yeah, that's it. What about next Wednesday? What about the last lab of the Wednesday? Is that an exam day or what's going on with that? Because it was a little bit of, are we having another in person or is that the last one?
No, we're not having any more in persons except for the final. And right now, what I'm leaning towards is everybody's going to do their final, can do their final on the 29th. Uh, Even though that's, of course, that's a Monday, so it's not everybody's day of class, but at least the face-to-face students can do it, even though their normal lab day is Wednesday.
Yeah. I have another exam scheduled on the 29th.
Gotcha. Well, I have several times. Like you can start at 9, you can start at 10, you can start at 11, you can start at 12, or you can start at 2.
What about the lab on the 24th? So we're not doing that on the 24th, right?
Yes, there's no more. Yeah, there shouldn't be any more labs done.
Yeah, I'm trying to look at the count. Okay, hold on. I got to look
If
at my calendar. Hold on. Let me get
Well,
my.
we'll have to talk about this in person. I'm losing a little bit of time here, so yeah, I'm posting an important chat message to everybody, and I'm trying to do that. That's why I'm a little not paying as much attention as possible. That and my
Okay, well,
eyes are about to kill me because I just finished mowing the grass and I have an allergic attack. So, uh,
okay. I just
but
have to
yeah,
figure out what to do about the 29th because I don't know if I can do it. I mean, I did,
well,
but I.
you can schedule it before or after. The whole reason I'm
Oh,
29th is because that gives me another class day in case someone can't make it. So you still have the
if I
option
can.
of doing it on the Wednesday instead of the Thursday. I mean, instead of the
Oh,
Monday. I just
okay.
most people will take the time to do it early.
Yeah. Okay. All right. That's all.
No
Thank
problem.
you. All right.
All right, I just posted that message. Like I said, I'll post some videos regarding that, and we'll have the following week. It's not a problem. Like I said, I just won't be able to do that. So, everybody, please look at the chat message that I just sent out. I'm going to send it one more time. So, all right. All right. So regarding the exam, so I just made practice test 7 available, and right after class, I'll finish making test 7 available. That's an online test, and that covers chapters 26 and 27. But like all tests, they're comprehensive. So that's going to be due Tuesday at 11:59. No, Monday at 11:59 p.m. I think that's the 22nd. So you have to get that done by then, but that is an online test that you're allowed multiple attempts, and it goes up through chapter 27. I may fit one more in before the end of the semester, and those only help you, and they only help you prepare for the final because all of them are basically comprehensive. So keep an eye on that. The final exam, as I've got it scheduled, you will have the options of on 4/29. You can come at 9 a.m., 10 a.m., 11 a.m., noon, or 2 p.m. If you cannot make that day, then 4:30 at 9 a.m. or 10 a.m. So that's your options for the final exam. I know I have a couple students that had issues that couldn't make it that day or even that week. Some will have to do it before. Some might take an incomplete for a couple days and then do it afterwards. But either way, like I said, that's the deal with how it's going.
Are there any after evening options?
Oh, you okay? So this is all for my face-to-face people. So I've got people in both classes, and yes, Logan, that was the same message for you. Sorry, I saw your text a second ago. You guys that are online, y'all are taking it whatever day that your lab instructor has you take it. But if you
So
want
then
to
that
take
would
it
be
during the day,
Tuesday,
you can. Yeah, I think she's leaning towards Tuesday, but I'm not positive.
the 23rd.
I believe again, I'll leave that up to her, but I believe that's what it is. Yes. Oh, actually, not the 23rd. I think it's the 20. It might be the 23rd for the lab final. I don't think she's doing the
Yeah.
lecture final on the 23rd. I thought it would be more like the 28th or 29th or 30th, somewhere around there. Well, not 28th, but 20.
On the syllabus, it says the 23rd on your syllabus for my class.
Yeah.
Okay. Yeah, that was a mistake earlier. If you need to take it on the 23rd, I can make it happen. It's not a big deal. I'm just saying the class is
I don't want to take it on the 23rd.
yeah, yeah. You like I said, the daytimes will be taking it. Those times I just said. If you guys are in a night class
So-
lab, then you're going to take it in your lab time according to whatever your lab instructor says. Sorry about that. I know that just
Okay.
made it worse. Anybody else
So
have any
I
questions?
have a question.
Go for it, Shonda.
Just to be clear, on Wednesday, the 24th, is that a day to take the final or not? The Wednesday, the 24th, because
It should not be.
that's the regular lab day for, I'm technically in the other class.
Yeah.
But I'm doing the online, but Wednesday, the 24th is the lab day for the other class. And so are you
No.
doing you're not going to be there?
No, we'll be there, but it's like a review session for you guys and possibly covering material.
So that's next week, not tomorrow, next
Right.
week
Right.
is a review. So
Yeah.
then you have the 29th and the 30th for the final.
Exactly.
Is that going to be at the testing center or at the classroom?
In the labs.
It's going to be in the lab.
Yep.
Okay. Okay, in the lab. So I'll probably have to do that. I don't
If you,
know.
like I said, if someone needs to take it a week earlier, I could make that happen. I have a couple people that are doing that. You're just going to get a different test. So, one, don't tell anybody about it because there's going to be some overlap. But two, don't ask anybody about it because there's going to be some overlap. And three, just know that it'll be a slightly different test.
Okay, are you going to post the times for the Tuesday and Monday and Tuesday exams?
Yes, I'm going
Okay.
to send, I just did that in the chat as well, so you can get that off of there. But
The
yeah, I'm going to
times.
post it as well.
I
Might be
have one
easier to scroll down and
question.
then take a snapshot of it with your camera.
Is the final gonna cover all the way to chapter 39? Or no?
No, the final's only going to cover the chapters that we get to cover, which I'm hoping will be chapter 30 and maybe even 31.
Chapter 30. Okay. Yeah. Yeah. If
Okay. All right. So last time we were working, we were in the chapter on sources of magnetic fields, which I believe is chapter 20. Yeah, chapter 28. And I had worked one Biot-Savart law problem for an infinitely long wire and found that B, the magnetic field of that infinitely long current carrying wire, was no, there's not a time for that, Shanda. I don't know if you posted that some time ago or just re-asking or what. But anyways,
okay. I just was wondering about that.
Could you
You
stop
said it was
asking that? I'm trying to do something.
okay.
Well, what were you saying, Shonda?
Just there's no time. Just be there at whatever time, Tuesday and Wednesday. I
Uh,
mean Monday and Tuesday, whatever time. There's no
no,
time
no,
posted.
I'm telling you, if you make a formal request and you want to do the final on the week before, we can set something up. I'm not making any of those kind of schedules online in real time.
I mean for the 29th or the 30th, there's no times posted to be there. Just be there at 9.
No, there is. I just posted them in the chat. Here it
I
is.
still don't. Okay. I'm sorry. I don't got it.
I'm doing it now. Actually, it might have went. Oh yeah, someone had applied, had actually texted me, so it automatically switched to to them. So I just sent one really important message to one person instead of every person. Angie's here, baby. Shawnee, Shawnee, Angie's here. Sorry. Okay, so there it is. These are all face-to-face tests for my face-to-face class, which you're welcome to do if you wish, but that's and that we just have to know ahead of time if you're planning on doing that, because I do not have enough computers and that kind of thing to really seat that many. But by doing it over 2 days and over these different hours, I should still be able to accommodate. This is Virginia Beach campus, and it's JC 21 and JC 26. And my dog is going crazy. All right. Sorry. So there's the exam schedule. As I said, it's the 29th. If you want to catch it on, actually, I said 4:30. I think that's 4:31. Come to think of it. Let me pull it up on the calendar just to make sure. Oh yeah, there's no 31 in April, so that would be a problem. Yes, it's 4/1, not 5/1, not 4:30. So everybody catch that, please. 9 a.m. and 10 a.m. On 5/1. Oh, my eyes are itching so bad. Whoa. Okay, so everybody catch that again. Again, that's really for just the face-to-face class, but if you guys want to, you're welcome to. That does mean probably Logan and Shonda. Shonda. How do I pronounce that? Okay, that's cool. All right, so let me get back to what we were talking about. So I said the law of Biot-Savart was what we were covering. I did the infinite line of current carrying wire and found B was equal to mu 0 I over 2 pi r, which is what we used in chapter 27 already, as if we knew it. We did that to find the force on one wire due to another wire, as well as just the force or the magnetic field around the wire, that kind of thing. So we started doing another problem, and it was a little more complicated. And I made, I knew I made some kind of mistake. I told everybody I made some major error, and I did. But it actually turned out the error wasn't as bad as I thought. Basically, the error was in the direction, not in the magnitude. So the actual derivation worked out fine for the magnitude, but the direction vector was wrong. So I'm going to redo that and then jump into Ampere's law. So let me start by sharing my screen. Anybody have another question since I rapidly ran through that? hopefully everybody saw. I'm going to post it one more time. Make sure I'm sending it to everyone. So if you happen to have a face-to-face class, or if you wish to do it at a different time during the day, that is one of your exam times. And here's the other corrected one. It's 5/1, which is Wednesday, not a Tuesday. I generally don't do anything on the Tuesdays or the Thursdays. But other than that, you can take your exam with your lab instructor. Okay. All right. So let me share screen. Anybody have any questions about the actual course material from last time or otherwise? All right, so this is the problem we tried to do last time. And like I said, what I did was mostly fine, but I was breaking the cross product apart a little bit, and in doing so, that gave me an erroneous answer. So what I want to reiterate is the Biot-Savart law says that there. Whoops, I probably should write in actual writing as opposed to dotted lines. So the differential segment of magnetic field is given by mu 0 I over 4 pi times dl cross rp minus rdl. That's the actual vector that we're using. You don't necessarily have to do the individual RPs and RDLs, but you can. So that's neither here nor there. It's just a separate option for you. Sometimes it seems really helpful to do the individual vectors by themselves. Other times it seems just cumbersome and needless. So I wanted to make sure you guys are aware of that. Again, the vector RP is a vector that's from the origin of whatever coordinate system you chose to the point P at which we wish to know the magnetic field. The vector RDL points from that same origin to a differential segment of the current carrying wire, the length of which is DL and the direction of which is the same as the current. So that's what RDL is. And then you can see R, which is RP minus RDL, is in fact the vector from DL to P. So if you can make that vector without the RP and the RDL, then that's fine. You can skip it. Okay. So when we look at this vector formula called the law of Biot-Savart, you can see it's kind of complicated, but I'm going to go ahead and go with it. What I want to remind you though is that A cross B is actually equal to it's normally that determinant, remember. So you could say it's equal to the determinant of a matrix I hat, J hat, K hat for the first row, and then AX, AY, which notice is the first vector. Oh, I said AB instead of AY, and AZ, and then BX, BY, BZ. That's a way to do it. There's a lot of different ways, of course, but there's also this wonderful way that you can use the magnitude of it and just your understanding of the direction to make the direction, in which case the vector is just A times B times the sine of the angle between them, where A would be like this vector and B would be like this vector. Excuse me, and that angle right there is just theta. In that case, of course, we would make A cross B perpendicular to it as drawn there, which you can see is a right-hand rule. Okay, so as I said, this Biot-Savart is the nastiest, most complicated looking equation and most complicated to use equation in all of calculus-based physics 1 and 2. I would even include the Schrodinger equation in that. So anyways, I'm going to show you a bunch of ways, obviously, to work it because we've already seen a couple ways already. This one right here is really nice. What I want to do is go ahead and set up the integral, and I'm going to say solution B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral. Now, I've already written out that dl is RD theta, theta hat, and theta hat, as you might guess, is literally perpendicular to the r hat vector, which is just a radial line in the xy plane that points from the origin to whatever point you're discussing. So it always points away from the origin. And then, of course, that would mean DL is 90 degrees ahead of it. So that's why I showed that right angle there and other stuff. So hopefully that'll help you. I'm also going to take and cover up that part so you see that the square symbol is actually behind the red line. So what we have right now is R, the radius of the actual loop, d theta, theta hat, that's my actual DL. That's going to be crossed with RP minus RDL. RP is in fact going to be ZK hat minus R cosine theta I hat minus R sine theta J hat. All that over. I'm just laughing at myself, getting frustrated with you. We're trying to talk and everybody asks me questions. I apologize. I should have been a better person. Anyways, I was just, I'm sorry. Okay, so you can see hopefully that the magnitude, if you look at that triangle with RP, RDL, and R as the legs and hypotenuse respectively, I hope you can see that the magnitude is in fact Z squared plus R squared, but it doesn't matter if you don't see it because you can still use your typical formula for a three-dimensional vector, and you will quickly find out that the R squared appears in two terms, so you can factor that out. When you factor that out, you're going to get cosine squared plus sine squared. Obviously, that's 1, so then it just reduces to Z squared plus R squared to the square root power, but we have to cube it. And remember, it's actually a 1 over r squared law, but we needed to make a unit vector out of the vector above. So we made it r cubed, so it would actually force that one to be like a unit vector. Okay, let me put that here. There you go. Okay, so hopefully that explains everything I was just saying. Now, when we go to do this, I can sort of do what I said to actually get the vector out, but that's where I made the mistake. So what I want to show you is looking from the side, we might see, for instance, oops, I wanted a different color than that. Let's see. So this is going to be my z-axis. That's my z-axis right there. What I have is this little black vector right here, and that's our DL. And then I have this little red vector And I should have marked the black vector pointing in the correct direction. I didn't put a head on it, in other words. So there's the RDL vector. And then I also have another vector that's black, and that one's the RP vector. Okay. Now I'm just going to arbitrarily call this angle. I'm going to arbitrarily call that angle that I just drew there. I'm going to call that phi. Okay. What I have to show in this case is, notice I'm looking at the picture above, but I'm looking at it where that DL is right in front of me and goes horizontally from left to right in the page. So I'm sort of looking at it at like a 45-degree angle so y'all can see what's going on. And in that view, the DL vector just goes straight into the page. So I'm going to do that as well by showing this. So right here is my DL vector into the page. The reason why is, notice that DL vector has to be crossed with that RP vector, which is this guy, or excuse me, that R vector, which is RP minus RDL. So when I cross product DL with R, I think you can see what's going to happen. DL cross R gives me a vector that looks like this. Actually, I missed it by just a little bit, but pretty close. Okay, this is in fact a 90-degree angle, and this vector right here is DL cross R. Okay. Everybody see that, and can everybody confirm that that is in fact exactly the right direction and magnitude, or not magnitude, but at least the right direction? Anybody have a question on how I got DL cross R being that vector? Okay, now I'm going to do something really crazy. I'm going to realize that that vector has a z component. So let's name this vector C. So this is C sub z. And let's also label this vector C sub x comma y. Okay. Because that is that light green vector is the vector that is in the xy plane. Even though it's up above it, it still only has x and y components, and it is in fact parallel to the RDL vector. Okay, everybody see that? I'm trying to do this specifically so y'all will understand exactly what's going on. So do you see how RDL is that bottom vector, and that's the same RDL that's in the top diagram? Everybody follow that? Anybody have any questions about that? It looks, I pulled up the chat just to make sure no one asked any questions. It looks like they have not. So does everybody see that? All right, now what I did was I did DL, which is that vector that sticks into the page. So you can imagine using my right hand rule like this. DL points the same way as my index finger. So going into the board, that means my index finger is pointing that way. Now I have to tilt my hand so that B can point in the direction of the R vector, which is that red guy. So I tilt it this way. Okay. Now my thumb points in the direction of DL cross R, which I think you can see, given my thumb's pointing this way, that's the direction of what I called vector C, which is that little purple vector. Okay, not the green one, not the dark green one or the light green one. And let's blow that up a little bit, just make sure everybody knows what I'm talking about. So is there anyone that cannot confirm specifically that the vector I've drawn here and labeled C, which I'm now going to write here, is C, which equals DL cross R? Everybody see that? Now, if you were to do a little bit of configuration, trying to figure out exactly where everything is, you would see that this line right here would create an angle right. Let me do a color. Actually, I think I'll stay with the gray. That would suggest that this angle right here is also phi. You see, it's like a railroad track. The RDL vector being one track, the dashed gray line being another track, and then the red vector being a piece of rebar laying across the two tracks, in which case those two angles are alternate interior angles. Therefore, since the railroad tracks are parallel, the alternate interior angles are in fact equal to one another. Okay, now that makes a 90-degree angle with the vector C. That angle phi up to the dashed line, then from the dashed line up to the purple vector, that whole angle is 90 degrees. Therefore, the one between the gray line, the gray dashed line, and the purple vector is 90 minus theta. And of course, the gray dashed line and the dark green vector make 90 degrees as well. So hopefully you can see that this angle right here is also phi. That's the key thing that I need you guys to follow. Does everybody get that? Okay. So now that I have all that drawn, I can make this vector calculation a lot easier. So I'm going to go ahead and write equals here. And of course, that's mu 0 I. I'm going to go ahead and actually, I'll leave all this alone right now. I'll put 4 pi on the bottom. I'm going to do an integral. Now, what I'm going to do is evaluate the cross product using this formula. Everybody see that? I'm going to do the cross product using this formula. Now, in doing that, what I need is the magnitude of the DL vector. So I'm going to put a fraction bar, and the magnitude of the DL vector is R d theta. Now I need the magnitude of the R vector. That's going to be the square root of z squared plus r squared. So that's the magnitude of the R vector. And now I need the angle between them. Okay, I need the sine of the angle between them. But I think everybody can see that that is in fact a 90-degree angle, because the DL is into the page like this, and the R vector is like that. Notice that's a 90-degree angle. So in principle, I'm doing sine of 90 degrees. I still have what's left in the bottom because that was just the cross product that I took there. So I still have z squared plus r squared to the 3/2 power. But now I've made it a lot less complicated, and I no longer have it a vector that points in a particular direction. So what I'm going to write next to this is just, let's write c hat, because I labeled that vector C over there. So I know exactly what direction the cross product is. It's the direction of C. So if I imagine taking C and dividing it by its magnitude, then I would have C hat. So notice I'm using that C right there, which is that vector right there, and I'm imagining as a unit vector, because then I can multiply it by this formula and not alter the actual magnitude of the magnetic field, which is important because the magnitude is given by the formula. Okay. So just to keep it as a vector equation, I just put C hat, and I don't have to do anything as far as integrating it. I'm just leaving that be. Okay. So now I can take and say, all right, I only care about the magnitude for right now. So B is going to be equal to mu 0 times I. And notice the sine theta being 90 degrees, theta being 90 degrees is just 1. And the R can come out in front because I'm integrating with respect to theta. And we're not sure yet what's going on with the Z and the R, so I can't pull that out yet. So I'm just going to pull this right here and then write 4 pi in the bottom. And I'm going to say the integral of R d theta turns into just d theta times, notice I have a square root of z squared plus r squared in the numerator. That's a 1/2, and then an exponent of 3/2 on the same thing down on the bottom. 1/2 minus 3/2 is negative 2/2, which is negative 1. So in fact, I can just say z squared plus r squared is now the denominator, and the numerator is just d theta. And of course, I'm going to integrate from theta equals 0 to 2 pi. Now, here's the problem. That is the entire magnitude of B. But I think you all can see, if you look at vector Cx comma y, at the position shown in the top, Cx comma y points down and to the right in that picture. If I were to consider this point back here, it would have a Cx comma y that would point up and to the left, would be equal in magnitude but opposite in direction, and therefore those two components would cancel out. So what I'm saying is for that angle theta and for the angle theta plus 180, the x and y components of the magnetic field cancel out. Since I'm going to do that for all theta from 0 to 2 pi, that means the actual x and y components of the resulting magnetic field will be 0. So due to theta causing Cx comma y vector, the angle theta plus 180 degrees causes a negative Cx comma y vector, so that the x and y components of B will cancel. Everybody see that? Anybody have any questions on that? It's very important that you get that, because it makes life a lot easier if you can, and it makes it almost impossible otherwise. All right. So we've just argued that, in fact, when I did that integral over theta equals 0 to 2 pi, the x and y components of the magnetic field are going to cancel each other out piecewise. For any given angle theta, you're going to have a positive cxy. And for the same angle theta plus 180, you're going to have a negative cxy that's going to combine with the cxy and cancel out. And that's true for all theta. So therefore, you have no xy components whatsoever in the magnetic field. That means only the z component will survive. And the z component is b times cosine phi. The z component of b is all that will survive integration, and that is gotten using, hopefully y'all can predict me, hopefully y'all can predict what I'm going to say, or predict what I'm going to write before I write it. Oops, I bet you didn't predict that. B sub z is just b times cosine phi, which is b times, notice cosine phi is adjacent over hypotenuse, and the adjacent has a length of r, so it's going to be r. Aggravating. So it's going to be r over z squared plus r squared square root, because that's the hypotenuse. Remember, cosine phi is adjacent over hypotenuse, and the adjacent is RDL, which has a length of capital R, and the hypotenuse is R, which has a length of z squared plus r squared square root. So that's what I'm using, and therefore I can now put R over the square root z squared plus r squared like that. Okay, so lo and behold, we're back to the 3/2. But that's okay. We can handle this, I think. Let me see. Yeah, back to the 3/2. So we had 3/2, and we had a 1/2 on top. 1/2 minus 3/2 would be negative 2/2, which would be -1. That's the z squared plus r squared by itself. And now I multiply it by 1/2. So we got 1 plus 1/2, which is 2/2 plus 1/2, which is 3/2. So we can go ahead and say b, whoa, there we go again. B, notice I put the vector symbol back on, is equal to, it's just the k-hat term that's going to survive, and I've got mu 0 I times r over 4 pi times the integral of d theta over z squared plus r squared to the 3/2, and we're integrating from theta equals 0 to 2 pi. And here is the trig substitution I'm going to make. Let z equal r tangent theta. So dz is equal to r secant squared theta d theta. You'll notice this is the exact same trig substitution I used on that first hard integral in chapter 21. And the process is identical. So we're just going to go with that. So now that I do that, I get equals k hat mu 0 I r over 4 pi integral 0 to 2 pi. And now I've got for d theta, oh, yeah, excuse me. Z equals R change theta, there you go. Okay, just got a little confused, but anyways, we'll work through this. I'm going to now say R squared is a common term inside of the square root or the 3/2 root. I can factor that out because Z is going to be R tangent theta and it's squared.
Professor
So it's,
Ryan,
yes.
are you? I think you're missing an R squared, like on the top
Uh,
or outside. Yeah. Because in B equals, you already had an R on the outside, and then there's an R on the inside of the integrand.
I did pull the R that was in front of d theta out front.
Yeah. But then you had
Oh, there
a
is another R.
yeah.
That's what it was.
Yeah.
Gotcha.
Is that the one that you're looking for? Because I
Yeah,
think the
that
R
was
squares
part of
will
the
cancel.
problem.
Yeah. Okay.
Yeah, thank you for that. Everybody see this? This R is what he's talking about, everybody. I just didn't copy it. Hold on, I got a pointer thing. This R is what he's talking about. I didn't copy that. So now what I have here, and this will help me out quite a bit. This becomes R squared and R squared like that. Okay. So now I have the R squared d theta, and what I have down here in the bottom is R, Z is equal to R tangent theta. I was wondering if I was supposed to make Z equal to R tangent theta, or if I was supposed to make R equal to Z tangent theta. But I think it's okay like this. So now I'm going to say 1 plus tangent squared theta, like that. This is all to the 3/2 power. So that means the R squared is going to become an R cubed in the bottom, which cancels out with the R squared in the top, and I'll just get a plain R in the bottom on the next line. And now I can fulfill my other part, which is d theta. D theta is going to be, why did I do dz? That's not supposed to be right. Z equal, let's see, if I look at theta, theta would be Z over R. That should be good. Ooh, maybe that's part of the problem. I actually was looking at using the angle phi, but I think theta is still what I want to do. Yeah, theta is still the angle phi. I don't want to go to that, so I've definitely got tangent equals opposite over opposite over adjacent. Okay, yeah, that makes sense. So yeah, it turns out that angle theta that I just defined is in fact the angle phi that we're talking about, and that has a fixed angle. Sorry about that. Notice the theta, it's okay. It's just if you'll notice, if I drew a diagram to represent this trig substitution, I'm going to draw it and then I'll just erase it real quick. What I would have is R, or excuse me, I'd have Z right here, and I'd have R right here, and then I'd have theta right here. That gives me tangent equals opposite over adjacent, which is Z over R, which is exactly what we got. And that makes the hypotenuse Z squared plus R squared, which is exactly what we got. So we see that theta is in fact already phi. And I don't think that matters at all because got to integrate with respect to d theta. So yeah, I don't have to do that at all, actually. Okay, so let's kill this for a second. I don't think I'm going to have to do this trig substitution at all. Notice z squared and r squared. If you find a relationship between z and r, it's not going to be a variable one. It doesn't depend on theta. In fact, it's always the same. So I really didn't have to do a trig substitution. I was thinking of a different problem when I did that. So I'm going to erase this part right here. Believe it or not, this is after I actually prepped for this today. So I've got d theta over z squared plus r squared to the 3/2 power. That's actually what my result is so far. And now I'm going to try to actually work out what it's going to be. I can go back to that previous line. So I'm going to take this out right here. So notice the z squared plus r squared is in fact completely independent of theta. So what's going to happen now is I'm going to say k hat mu 0 I r squared over 4 pi times z squared plus r squared to the 3/2 power. And I apologize for being such a bonehead, not realizing that and trying to confuse it with the previous problem. And now all I have left is the integral from theta equals 0 to 2 pi of d theta. Does everybody see that now? Does that make sense? Hopefully it's a lot less confusing than what happened before. Now that I have that, I can integrate it. You know that the integral of d theta from 0 to 2 pi is just going to be 2 pi. So this part, oops, let me write it in red so it stands out a little bit. This integral is just 2 pi, and that's going to cancel out with the 4 pi down here. So I'm ultimately just going to get mu 0 I over 2 for that particular portion. So now I can write equals mu 0 I r squared over 2 z squared plus r squared to the 3/2, all of that times k hat. And that is the magnetic field in its entirety. Okay. Now, the main part about that is, yeah, that's kind of complicated, but it's a formula that we could in principle use. In fact, let me see. I'm going to check and see if the book got the same thing, because the book did a very similar problem. It got mu 0 I. It used a different set of variables, but basically mu 0 I r squared over 2 r squared plus x squared in parentheses to the 3/2 power. So yeah, it got the same result I did, which, is good because I expected to, but at the same time, it's always good to check, especially when I made a mistake in the middle. So now that I have that, I want to show you a special case. Specifically z equals 0. In that case, we get b is equal to mu 0 I. Now notice what happens when z is 0, I get r squared to the 3/2 power in the bottom. That's going to make the r squared become r cubed, and r cubed in the bottom with r squared on the top gives you mu 0 I over 2 r k hat. And that's exactly right. And what that tells us is a single loop of current will give us a magnetic field magnitude mu 0 I over 2r at the center of the loop. And it's consistent with the right hand rule, so that if you grab the wire so that your right thumb is going around it in the direction of the current, then your fingers poke through the middle in the direction that the magnetic field would point. So if it's coming from below, that would mean it points up and uh, out of the loop. But if it's pointing down, if your fingers are pointing down because the current was going counterclockwise, or excuse me, clockwise, then your fingers would be pointing down through the middle. So the magnetic field would be downward for that case. That's very important because that lends itself easily to some very complex problems. Anybody have any questions on that before I move on to the next quote unquote complex problem? Okay, I'm going to recap that. So if you have, let's do this. I am going to draw a coordinate system like this and this. Now I'm going to draw. Whoa, no, that did not go well. Okay. Well, great. That one worked really well, but that time it didn't autocorrect. It was supposed to autocorrect. Don't make me mad. Okay. So there's a loop of wire. Let's imagine for a second that the current is going that way. Darn it. Let's imagine for a second that the current is going this way. So that means right here, the magnetic field points up. And it's equal to mu 0 I over 2r k hat. If the current was going this way, then it would be B is equal to negative mu 0 I over 2r k hat. So that's how the right hand rule works with this. Anybody have any questions on that? Now, the big thing that you might not have noticed is notice the integral. Let me get out my little pointer. Notice the integral was the integral d theta from theta equals 0 to 2 pi. Therefore, we got 2 pi. What do you think that answer would have been if it would have been, say, a half a circle instead of a whole circle? What would have been what would have been the value of that integral for a half a circle instead of a whole circle?
Pi.
Exactly. And what about for a quarter circle?
Pi half.
Exactly. So what we can realize is, I'll put it this way. For any radian angle, B magnitude is equal to mu 0 I over 4 pi r times theta in radians. Okay? Which means B quarter is equal to mu 0 I over 8r. because of course, like we just said, if we did a quarter circle, it'd be pi over 2. Pi over 2 working with the 4 pi in the denominator, the pi's cancel out, and the 4 is multiplied by 2 to give us 8. So that's the big thing that we're going to do. And for instance, your book does an example. Let's do like this. Let's say example. What is B at the origin? So here's going to be our little drawing of our axes. I'm going to draw an axis like this, like that. And now what I'm going to do is imagine a current carrying wire coming in here. Turn it. Let's do this. I'll draw a circle first. That might make it easier. Okay, that looks pretty good to a circle. So I'm going to use that. Now I'm going to erase the part of the circle that I don't want, which is this part, this part. And just for good measure, make sure I get rid of that little bit and that little bit. Okay, now what's going to happen is my current carrying wire is going to do this. So I is coming in from this side and then going around that way. Now, according to the right-hand rule, if this is the x-axis and this is the y-axis, then the z-axis has to come out of the page. By the way, this is supposed to be perfectly straight up. It does not appear to be so, but that's a bad drawing, not a reality. So let me try to make it a little better. Okay. So we've got that. And of course, like I said, Z would be coming out of the page. So based on what we just learned, the solution should be right-hand rule suggests B points into the page, I period, E period, in the negative K hat direction. And its magnitude is mu 0 I over 8R. So B is equal to negative mu 0 I over 8R, where that's R and that's R, and a K hat. Any questions on that? Now, I'm sure you can see how the quarter circle part came, but the part that you might not be able to see that's not necessarily obvious is notice what happens for this portion. So when you're looking at this part and this part, notice DL and R are parallel. for these straight parts, DL is parallel to R. So DL cross R is equal to 0. So the fact that the current at one point is going towards the origin, and also in the other point is going away from the origin, either one of those is basically going to create a magnetic field of 0 because the cross product gives you 0. So that's how that worked out. In fact, we can soup this up even more and say, here's an example. This time, we're going to say current carrying wire comes in, makes a quarter loop, goes out, makes another quarter loop, goes out to, darn it, erased my own work. Makes another quarter loop right here, and then comes back here, makes a quarter loop, and then goes back. So we've got a wire coming in with a current here, and that same current I going out over here. And what we want to know is what is the magnetic field right there. Okay. See, that looks really, really nasty and virtually impossible to do, but it's actually not hard at all. I'm just going to label this as R, R2, R3, and then actually let's call that R4 because it seems to be bigger than the other one. And this would be R3. So if you look, R1, or yeah, I'll go ahead and call that R1. The one whose radius is R1 and the one whose radius is R2 both create magnetic fields pointing into the page, which would be in the negative k-hat direction. And the other ones point in the positive k-hat direction. So what we're going to get is B is equal to, let's go ahead and draw these axes just so there's no ambiguity about what the right answer is. There's my x-axis. There's my y-axis. Z is out of the page. So we can say B is equal to mu 0 I over 8 times, let's do that, times k hat, and I don't know why I just switched to black all of a sudden, but I guess I would just go with it. So it's going to be k hat, and the only ones that are positive is R3 and R4. So 1 over R4 plus 1 over R3 minus 1 over R2 minus 1 over R1. And that's it. Anybody have any questions on that? All right, yes, go ahead and chat or put in the chat window your first and last name so I have you for roll. I'm going to go ahead and start off by showing you Ampere's law. Much simpler version. than the BO sub art law, and I'm going to do it with a much simpler example of a straight infinitely long wire, which we already know the answer to. So let's start by drawing a coordinate system. I know we don't have much time, so I got to fit in at least one of these examples. There's my X and Y axes. Actually, I'm going to do it slightly different. I'm going to make an XYZ plane like this. And this is going to be X. This is going to be Y. This is going to be Z. And I am going to imagine my wire is like this. Goes on to negative infinity. Goes on to positive infinity. And in fact, the current is I. And over here, a distance R away is P. And I wish to know the magnetic field there. Ampere's law says this. The closed integral. Notice it's a closed integral. It's got a circle on it, just like Gauss's law did. But this time it's not a surface integral. It's a path or line integral. Okay. And we're taking the dot product not with dA, but with a differential line segment that's supposed to be, if you're doing Ampere's law like I'm getting ready to do, which is in a way that we can extract the magnitude of the magnetic field from the integrand to find the magnetic field using certain symmetries, then what we want is B to be either 0 on the line or exactly parallel to the line. If it's not 0 on the line or exactly parallel to the line, then you want B to be perpendicular to the line so that that part of the integral gives you 0. The other side, turns out, is just equal to mu 0 I enclosed, and there's a sign convention associated with that where your path around the path, the direction you go, has to obey the right-hand rule, so that if you curl your fingers around the direction that you're integrating, your right thumb is pointing in the direction of a positive current. If the current's going the other way, then you have to call it a negative current. So that's the key to all this. So what I'm going to do is, for starters, I'm going to put this R a lot closer than it was because that makes the circle too big. So let's do this. I'm going to erase that, and I'm going to say R is right here. And that's the point P. And that's my x-axis. So what I'm going to do is I'm going to create a path around the magnetic field, or excuse me, around the current carrying wire in a direction that should mimic the behavior of the magnetic field. So this right here is called my Amperian loop. And obviously its radius is R because I wanted it to go right through that point. And in fact, I'm going to integrate around it consistent with the right-hand rule so that the B is actually parallel to it. So my hypothesis is that B, the magnetic field as a result of this current carrying wire, is going to be some B of R times theta hat, because remember, theta hat at the x-axis points this way, at the y-axis points into the page, at the negative x-axis points this way, at the negative y-axis points this way. So it literally mimics the tangent vectors to the Amperian loop. Okay. So theta is parallel to the DL vector. So now that we have that, we can say left-hand side. I know I only got like 5 minutes left. So left-hand side, the closed integral of B dot DL is equal to the integral of B of R theta hat dot R d theta theta hat. Okay, and this is of course going to be integrated from theta equals 0 to 2 pi. And hopefully the RD theta looks enough like the previous differential line segment for you to understand exactly where it came from. But the main thing is, because I'm evaluating it on R and R is a constant over all of theta, then I can pull out the B of R and the R, and then I just get an integral from theta equals 0 to 2 pi of d theta times theta hat dot theta hat. So I just made use of the linearity of the dot product so that I could pull all those non-vector things out in front. In other words, I pulled B of R, and d theta all out in front of the dot product. Then I just left the two vectors to have a dot product party. And the two dot products, or the two vectors had their dot product party. And that resulted in theta hat dot theta hat, which is 1, or a drunk owl. And ultimately, now I just get 2 pi r times B of R. So remember Gauss's law, the left-hand side always became the electric field times an area. Well, with Ampere's law, it's going to, no problem. I just read Michael's chat. But in Ampere's law, it's going to become a length times a magnetic field, or a series of terms where it's a length times a magnetic field, so on and so forth. That's the left-hand side. Now, the right-hand side, especially in this case, is super easy. The right-hand side is just supposed to be mu 0 times the current that's actually passing through any surface that is bounded by the Amperian loop. So notice my wording there. The mu 0 times I enclosed needs an I enclosed, and that I enclosed is any current that goes through a surface bounded by the Amperian loop. So you could imagine this Amperian loop being a round bit of plastic that you dipped into a solution of water, dish detergent, and a little bit of glycerin. Hopefully you know that reference, but basically when you do that and then you pull the loop out, you can then run with it and make little bubbles and stuff like that. What I'm saying is that Amperian loop is the plastic loop, and any shape that bubble makes will be acceptable for us to determine the current going through it. So if a current pierces that bubble, that's the amount of current enclosed. I'm going to imagine the surface being a flat surface in this particular case, because it's easy, and it's virtually always easy with a flat surface. In this case, that means the current enclosed is consistent with the right-hand rule, and it's actually equal to mu 0 times just plain I. Okay, now because I put that so close, I need to block it off. Now I can set the left-hand side equal to the right-hand side. And with this, I get 2 pi RB of R is equal to mu 0 I. And therefore, B, using our original hypothesis, is B of R theta hat, which is equal to mu 0 I over 2 pi R theta hat. That's how we use Ampere's law. Now, Ampere's law, in order for us to use it this way so that we can extract the integrand, it has to have certain symmetries. The symmetries are, it's got to be an infinitely long straight wire. That's the one you just saw. It's got to be a relatively long solenoid, which is like a long wire as well. Mainly all it means is stay away from the edges, the ends of the solenoid. So that's a electromagnet. You know how you wrap a wire around a nail and make an electromagnet? That shape that you make with the wire is a solenoid, solenoid. And the third shape is a torus, which is that solenoid put into a circle. So if you take the solenoid and bend it after you pull it off the nail, you bend it to make a complete circle. That's a solenoid. So the symmetry is required to use it this way. It's always true. It's Ampere's law, not his helpful hint that sometimes works. So the symmetries are infinite straight wire, infinite solenoid, are a toroid, torus, something like that. Okay. All right, that's enough. You guys are free to go. Remember about Thursday, I will post some videos and send some emails about the final exam and the tests and all that good stuff. So have a good one, and I will see you guys next time. And again, I apologize if I lost my poop for getting frustrated with trying to talk and having a bunch of questions. That's on me. Sorry about that. I should do better. Have a good one, everybody. Thanks for coming.
You supposed to put your name in the chat, right?
Yes, please do, Shard. Yeah, everybody, if you haven't already, put your name in the chat first and last. I thought I saw everybody had done it. That's why I didn't repeat, but there might have been some people that missed. So, anybody have any questions?
Yeah, I still want to email you about. I emailed you about the extra credit.
Gotcha. I will check that. Actually, let me check it right now while you're here. That way, I can make sure I get it done this time. Because last time I went to do it and then I couldn't find which one you were talking about.
Yeah, I think you said you were sick or whatever. And
Yeah, I also got sick, so that was another problem. Okay, so I can do a search for your emails. Oop, that is not the one I got. Okay. Did you possibly send it to my Canvas email?
I know I sent it to the email I always email you from.
Okay, I see what's going on. Evidently, I've been logged out of my TCC account. I have a little red mark by it. Yeah, that's what it is.
Let me see.
I just got to log back in real quick. It's sat for too long.
Okay, I'm gonna show you the date and stuff so you see which day.
No problem. Hope this works. Darn it, come on. Okay, this should do it. Yes, did it.
All right, find it before me. Hold on.
Okay, now it's letting me do it.
You find it?
Mm-hmm.
Uh,
Yeah, it's just pulling up now. It's just taking a long time for it to approve. Let's see if it did it over here. There it is. Not there, not there. Let me look for it over here then. Okay, now I can see it. Before it was saying extra credit, but I couldn't see the actual email. Partial field capacitor. Okay, that's cool. So let me go in there now.
No class on Thursday, right?
That's correct. Yes, sir. Glad you saw that.
I was looking through a chat just now.
Okay, I found one of them. That's not it. There it is. Yep, it had a deadline of March 22nd. I'm going to just erase the deadline. Actually, let's make the deadline.
I submit it tomorrow morning as soon as I get out of lab.
No problem. I'm just making the deadline like the end of the semester. That way, it's just a little easier. Sometimes people will submit something way after the semester's over, and then I can't do anything about that. All right, I did it now. You should be able to find it. I wish I could tell you where it is, but I suspect you know.
No, I can find it if it isn't on the homepage, whatever. I just
That's
find
cool.
it.
No problem. I got that taken care of for you. Sorry again for it taking so long.
Good. Thank you. All right, you have a nice day. All right.
You
Hey,
too.
Professor. I
Yeah,
wanted to
Mike.
ask you again. I joined like right after you said what we're doing tomorrow. It's like
Mhm.
not a lab, but
Yeah, it's I'm covering new material, and what I'm probably going to do is I'm probably going to use a good fraction of the lab time and count it for lab and lecture, so you won't have to
okay.
come back at 3 for those
Okay.
that
Yeah.
have lecture. You're welcome to attend that, or you're welcome to skip it, whichever one you want to do, because it's not going to be a lab, so it's not on you to do that.
Okay, I got you. Yeah. That's cool. Oh, also, yeah, I think I might take you again over the summer for physics too, because like even if we're doing the final and my grade goes up to a C and I pass, I think it would be good for me to retake you.
Great, gotcha. Well, that's
Yeah.
cool. That sounds good.
Yeah.
If you just want to sit in, you're welcome to do that. I can let you do that without going through the formal process and
Okay.
things like that too. So just let me know.
I got you. And also, is it like if you retake a class, you get like your new grade if it's higher or replaces that old one for like that class?
I think we have a multiple F policy at TCC, but I haven't looked it up in a really long time. So I would suggest you look in the manual
Mhm.
for it. But it's often called like a multiple
Yeah.
F policy or something like that. Or you might call the
Okay.
registrar. They probably know right off the top of their head.
Okay, that's cool. All right, thanks, Aaron. Yeah, I'll see you
All right.
tomorrow morning.
All right. See you, bud. See you, Micah. All right, that looks like it. This will stop share. End.